Alert data is data that is produced by IDS and IPS systems. IDS and IPS systems are designed to root out signs of malicious activity on the network. Needless to say, their alerts receive significant attention within the SOC. Security professionals are not in agreement on the distinction between IDS and IPS, though. One school of thought is that the distinction is not about the tool itself, but how it's deployed. To provide intrusion prevention, an IPS must be deployed inline so that it has the ability to drop traffic that it classifies as malicious. If the system is deployed using port mirroring or network taps, then it is considered to be in IDS mode. Also note, if an IPS system is connected inline and is configured with all drop responses disabled, it is then in IDS mode. This distinction is very important to the network security analyst. The analyst must understand if the IDS is capable of dropping malicious traffic, and the analyst must also know how to examine the alert data to determine the actions that the IDS has taken. When analyzing a particular alert, the analyst must determine the efficacy of the alert. What conditions cause the alert to fire? As an example, what if the IPS is reacting to a string pattern in an HTTP request, and if the rule defining the string pattern is associated with an IIS vulnerability, but the target's web server is running Apache, then the analyst can conclude that the exploit was not successful. Even if the exploit was not successful, the analyst can correlate the alert with other alerts and other data. Are there other alerts associated with the same source IP address? Or are there other web servers that were targeted with the same exploit? And also, is there any session data showing other connections from the same source IP address? Security Onion includes both Snort and Suricata as rules-based network IDS operations. And it also includes Segwell and Squirt as IDS event consoles. Both tools provide analytic capabilities concerning the IDS alerts, but also allow the pivoting to other applications. This screen clip shows the alerts in the Segwell real-time console. The alert that is selected displays the message malware backdoor, and this is a backdoor access attempt. Now on this screen, the snort rule that triggered the alert is displayed as well as the packet details of the trigger packet. The analyst can then inspect the snort rule and see that it triggers when HTTP URI contains reference to PHP myadmin serversync.php. The snort rule also contains reference URLs and the signature ID. By examining these references further, the analyst can learn more about the vulnerability for which the alert is concerned. You can see that this signature ID contains a Trojan horse inserted into the myPHP admin string. And looking a little bit further at the packet data, there was an HTTP GET request for third-party PHP myadmin serversync.php. The important question here is, how did the server respond to this request? Logs of client requests and server responses are transactional data. Bro records this HTTP transaction data and also provides an interface to the query of the Bro logs. The security analyst may then choose to pivot from Segwell to ELSA, querying on the alert 5-tuple. Let's go ahead and take a look at that information. Here's the output from the ELSA query. It contains some of the same information in a more readable format. From here, the analyst can pivot to CAPME to decode the PCAP, or packet capture file, of this TCP connection. Let's take a look at that. In this output, you can see HTTP GET requests for this connection, and in this decode, an analyst can see that the server responded with a 404 not found message. This is because the target URI was not found on this server, so in essence, this exploit missed the target.